people who are interested in presenting for second semester. And the way we do this is we have a senior presenter and ideally paired with an ECR or a PhD student. So if you have good PhD students, if you have good ECRs, or if you have people who have an interesting story to tell, whether that's in industry or academia, please pass their names on to either myself or Laura, who will be our first speaker, via the PhysChem division email, and we'll get them on the list, because we want to have a nice diverse array of topics. We don't want to just be CompChem. We don't just want to be experiments. We want a big range of things to come. So even if you think it's a bit left field from what other webinars are, throw it forward and we'll put them on the list to try to get everyone an opportunity to speak. Following up from that, I'd like to introduce our first speaker for today, and that's Dr. Laura McKemmish. Now, Laura was giving me a spill of her own bio before I got started today, and she basically said, I've been involved with the physical chemistry division since honours and have been doing activities with it since 2012. Look, Laura is an amazing physical chemist, and she's an amazing scientist who's driven both community within the PhysChem division since I joined the executive committee last year, and a range of other things. I'm going to leave it brief because, as Laura put it herself, as an academic, she's going to introduce herself anyway. So Laura, I'd like to hand over to you. And if everyone who's not speaking could just make sure they're muted and have their videos off, ideally, until questions. And there'll be space for 5 minutes questions at the end. Right, Laura, take it away.
Thank you. So apparently I've been here long enough that I'm now a senior member of the committee, senior member of the division, which anyway, we'll see how we go. And I really am absolutely delighted to be able to present to you guys all today. And I'm aware when I was putting this forward that I've got some people that have probably never heard me speak. Hopefully we've got some young PhD students in the audience. And I've got people who have probably heard me speak on an annual basis for at least the past 5 years. So I can promise we've got some new results that are coming out, mostly from my student one, who's in the audience today, about what model chemistry you should use when doing harmonic vibrational frequency calculations. What do you tell the organic chemist to do? Not B3 lip 631 G star. And importantly, what errors can you expect when you actually do this? And just because it's me, I want to do a little bit of astronomy because it's fun. Okay, next slide. So last year we had our first group retreat in May 2022, and our group has grown since then, so that's really exciting. And for those of you who maybe don't know me and my background, my research interests as well, this is how I describe what kind of computational chemist I am. I'm definitely small molecules, astrochemistry, method development, benchmarking, so very much on the gas phase spectroscopy that's really detailed most of the time. And today is probably the less detailed, so we're going to get spectra of thousands of molecules and figure out what methodologies we're going to use there. And I've just put the pictures vaguely where my group members are researching. Yeah. So what is astrochemistry? Astrochemistry is basically anything that's not on the Earth that has molecules in it. And so I love astronomy, and if there's molecules in the astronomical situation, then I might be able to say something about it, because all of it, we use spectroscopy to get the information about it. And we'll come to that to a moment. But solar system planets, stars, exoplanets, so they're planets around stars other than our own, and interstellar medium. So the big hot news at the moment is exoplanet atmospheres. So there was recently a telescope called the James Webb Space Telescope that launched, and we're getting better images of what the composition of exoplanet atmospheres are. So you've got a rainbow from the sun, and then it's absorbed by the atmosphere, and then we see the absorption spectra here on Earth. And we often know what dominant molecules to expect. So water, carbon dioxide, maybe, that's a recent discovery, methane, etc. But one of the things that I was surprised about when I first joined this field is that there might be really weird molecules. So when I say titanium oxide and vanadium oxide, titanium oxide is one of the top 5 molecules to astronomers, I would say. And I am talking diatomic TiO that you give to a first year and they go, what's the valency? What's the component of this? They're the sort of things that I've done a lot of work on. I'm not going to talk too much about them here, but the key is no matter what you're doing, it's all about spectroscopy and astronomy. It's all about getting the exact absorption line of molecules, and then figuring out what that means. And so we've been doing this a little while. This is a low resolution detection of titanium oxide from space. Yeah, we've got a wavelength on the x-axis, so this is the visible region. Transit depth, you can just think about it as the absorption spectra. We give the astronomers data, they put their data into their models and check they've got all the physics right, and then they can identify if there's molecules in the atmosphere of these planets. So the really important part and where I come into this is that the astronomers need spectral data from chemists to identify molecules and quantify their properties. And I would say you need both computational quantum chemistry, solving the Schrodinger equation, and you need experiments. So it might be, look, I am a computational chemist by training, but the models that I do in this field, you need the experiment and you need to put them together in the best way you can. And if you've heard me speak, you know, a while ago, then you might have heard me speak about the rovibronic spectroscopy of transition metal diatomics, where you do electronic structure calculations, so what most people would call quantum chemistry. You have experiment, you put it into a nuclear motion program. So this is actually doing the bit of the Schrodinger equation that we normally ignore. Normally we just go, here's the electrons and da-da. When you want the details, you need to go, how are the nuclei rotating? How are they vibrating? And then we get all that data together and give it to the astronomers in what's called an XML line list. And yeah, this is hundreds of thousands of lines, millions of transitions, and this is the type of data that astronomers are used to getting from us. So the one that I produced in 2019, which the astronomers were asking for it quite a while, and I'm like, I'm getting there, I'm getting there. So we've got this here, and the this is probably the figure I like best for this audience. Up the top is experimental data. And I would have thought that those bottom ones were just noise. So the big signals are obviously signal and the bottom ones were just noise, until we actually got the model where it turns out those big lines are the main isotopolog, and all those small lines that you can see, we can model them really precisely as the minor isotopologs in titanium oxide. So we didn't fit that at all. We didn't fit the isotopologs. We definitely fit the main spectra. Otherwise, you don't get the sort of accuracy you need. But yeah, we can predict this to subwave number accuracy. And that subwave number is needed for the astronomers for their new technologies, but not the technology I'm going to be talking about today. So that was the big thing in the past. And it's still emerging, but I'm going to go on to a different story today. And I'm up to slide, whatever slide number I'm up to, 14. And this is my first alien slide where I've actually got an alien. And that's because when you talk to the public about this, and if you talk to astronomers, look, the big goal of this is we want to find life elsewhere. And that normally means finding biosignatures. And I think the important distinction that most people realize a biosignature is a molecule that's produced by life. But the key is that it's not produced by geology and it's not produced by photochemistry. So we say life is the hypothesis of last resort. You figure out what else could have caused whatever you're observing, and if you can't figure out anything else, maybe it's life. And hopefully my video will work this time. Oh, yep, good. Probably 30 years we'll find something that looks like a biosignature, and then we'll spend at least the rest of my life arguing over whether or not it's a biosignature. So that's the one I like to say. And the fascinating thing, this was 2016. Oh, next slide. Oh, and the fascinating thing at the back here is that is phosphine, which if you've been paying attention to this field, in 2020, phosphine was detected tentatively in the cloud deck of Venus. Phosphine is a good biosignature because you try volcanoes, you try meteorites, you try lightning, you can't produce enough phosphine because it's destroyed so quickly on Venus. Look, subsequent observations, I would say that it's pretty, the consensus is it's probably not phosphine just because it might be a different molecule or the telescope was playing up. I think it's still a little bit unknown. In Venus, we can send a probe, obviously, and just check, but we can't do that in general. And this is a good example of the type of thinking that motivated the new innovation in our group that I'm going to focus on today. So look, doing the really high precision work like for titanium oxide, that took years. And anytime you want to do a molecule, it takes years and you need to know what molecule it is. But there's actually a value in approximate spectra. So I'll give you the example. Ozone is a potential biosignature. So if we find ozone in an exoplanet, someone's going to go, wow, what is this? But if the astronomers are looking at low resolution, they might not realize that the ozone signal is very close to all these other molecules like methane, NO2, and similar absorption bands are actually found in another 600 Schnops-like molecules. And so it depends what accuracy do you have the spectral signature. We just get a blob on the spectra and it's not, this work isn't at that wave number resolution. This is much more low resolution stuff. And there's going to be an ambiguity. And I can tell this audience that astronomers are astronomers and they're very good at their field, but they don't necessarily realize things that chemists, we just know intuitively. Like if you're trying to detect methanol versus propanol using the COH stretch, well, that's not going to be very distinguishing. And so we need to communicate this sort of data to astronomers to figure out what's, to make sure they're reaching the right conclusions. And so we can do this manually. I teach my first year students how to do this. This is WebMO. You create an input, you get the answer, and then we find out that the OH stretching frequency for this molecule is predicted at 4,000, and we're like, yeah, that's wrong. And then we apply a scaling factor, so it's an OH stretch, and we get it roughly right. Now, then I was fortunate enough to get one who's almost finished his PhD. And I said, I want you to do that 10,000 times, not manually, and tell me the errors. And so the starting point when we were starting here was like, well, okay, what method do we use? There's a mess of methods, levels of theory, basis sets. And the first question we asked is obviously, what does the literature tell it? What does the literature tell us? And the first thing, and look, I just wanted to know which method and basis set we should use. But when you actually look at the literature is focused on scaling factors. It's all focused on, if you pick this method, what scaling factor do you need to match the calculated harmonic frequencies with fundamental frequencies? And this is really important. This is ethanol in more detail than we did before. The experiment's at the bottom. The unscaled is in that dark maroon and the scaled is in blue. You can see that a scaling factor is really important in turning it from a nonsense prediction to something really useful. And so that's what the literature was focused on. And so we started by actually doing a meta-analysis. I say one did the really hard work here of actually looking at all these papers, getting out all the scaling factors, hundreds of methods and basis set, 14,000 scaling factors that span the whole Jacob's ladder. They span the density, they span the basis set space. Obviously hybrid, double, triple zetas were the most represented, but it's all the way, it's fairly diverse. We could use this to get a promising method and basis set combination, but there was definitely a lack of the contemporary options. So modern basis sets weren't necessarily included, modern functionals weren't necessarily included. And also when you were trying to compare one result to another, they used different comparisons. And so we couldn't consolidate all this data and go, what method should we use? And we decided based on this analysis that we needed to perform our own benchmarking to determine the most appropriate method basis set combination. And just to clarify, when you're going from theory to experiment, you've got all sorts of errors coming in. One of them is you've got an anharmonicity error because you do that scaling and you're doing the harmonic frequency scaling it. You really want to calculate the anharmonic correct fundamental frequency, but you don't. And then you've got the model chemistry error. And so the second thing we did, so the first paper was the meta-analysis of scaling factors. The second paper is and one of you in the chat, feel free to add the papers if you'd like. The second one was figuring out a good benchmarking set. So the most common benchmarking set was created by Leo Radem and co-authors, and Popel, I think, also had a say in that in about 1996. So we thought it was time for an update. And we created 141 molecules, a whole bunch of experimental frequencies, updated them to make sure they were the correct ones, updates. And we also did very high level theoretical calculations so that we could understand that anharmonicity error. And so Vibe Freak 1295, we've got the previous experimental data, we've got the CompChem data, we need scaling factors to compare. And we actually, when you do this scaling factor and you use our data set, you end up with a median error of 16.1, but most people will report this as an RMSE of 33 wave numbers. And if you're looking at the box and whisker plot on the left, you see that the RMSE is way outside even the 75th quartile. So I say that because there's outliers that dominate, the median is a more useful method of characterizing the errors in these molecules. So that's not what's in the literature until we published, but I think hopefully you'll look at this box and whisker here and agree that the median error is going to be more indicative of what you could typically expect in terms of performance. And when you use the median error, it's actually quite clear that you can get halving of your error by literally using 3 scaling factors for the different chemical regions rather than 1 scaling factor across the whole range. So frequency specific scaling factors, we definitely encourage to give better performance. Remember, this is just to do with the anharmonicity error. This is if you don't do anything except say really good theory, experiment and do the comparison. And that was the second paper. And then the third paper, we did the obvious thing and said, well, okay, with a whole bunch of density functional theories, with a whole bunch of basis sets, what are our median errors? And this is sort of the distribution here. And you can see that hybrid double zeta, the ones that most people use, are pretty good. By the time you get to double hybrid triple zeta, there are choices which get you to the anharmonicity error, which is really the best you can do if you don't go to a VPT2 higher level vibrational treatment. But you can see it also really matters which one you pick. You pick the wrong combination there and your result is going to be horrible. And if you pick the right one, you've got much better errors. And this is the guts and glory of all the details here. Blue is good, red is bad, in between is okay. And it's all of the details are in the paper, but this is our recommendations for very high accuracy and superior performance. We do give a variety because we also considered the number of outliers, the computational time, the reliability, and what we mean by reliability is actually do the calculations finish. And then the routine exploratory calculations here. So the winner in our thing was B971-631G star. Yeah. Should you use B3LIP631G star? I suggest not, because otherwise you might get reviewers that hate you. But honestly, for vibrational frequency, the performance is reasonable. And it's only for the other properties that the performance is inferior. And that's why we didn't include it in the table. So I'm going to come back to this one at the end, but it's, yeah, that's the da-da moment. But in terms of, if we go back a little bit to the astronomy and tell you an interesting story, and I know I've only got a short amount of time, so I'll be pretty quick on this one. This was the one that we picked for our study here. We want a hybrid, but we've got the computer time, we're going to go for a triple zeta here and get that increased performance. And then Juan's PhD is wrapping up, and Maria Pettyjohn, who's starting, is sort of she's doing confirmers and doing a new direction on this project that I'm sure I'll be talking about when you hear me next. But there's an automated way that we can do CompChem en masse. It can produce useful data, and you might have seen me talk about this one before, but what you probably haven't heard me talk about is the actual experiment, like the actual what this happens in practice. So this was a detection in, I'm going to say mid-2020. They found carbon dioxide. And then the big question all the astronomers had was, what is that signal there? There's an unknown signal, what is it? And the astronomers, seriously, everyone was talking about this in that little exoplanet community. And the important thing here is, as chemists, we can actually say, there is no CH stretch here that's significant. There's no NH stretch, and that actually tells us a lot about what molecule it could be. And we looked at our approximate data and came up with this set of molecules. And honestly, they're all looking a bit weird for the data. One probably has more to say about why we excluded that one, but there's not great options. And that's because at 2,500 wave numbers, there's not much there in terms of fundamental stretches. And so we needed to go to overtones, and here we did some quick BPT2 calculations. We came up with a whole bunch of molecules here that it could be. Ozone is obviously one that struck our interest. Apparently this other one is formed in the interstellar medium. And then we got the paper that said it was SO2. So someone found it, and it turned out that it was actually in the set of molecules that we had, that astronomers had really good data for. So there's about 100 molecules that astronomers really know what's going on. And then every other molecule, they don't really have a lot of data. Now, this is only one band, and they might have the same problem that they had with phosphine. So you've got to be careful. And so this is their prediction of what will happen if they look at larger wavelengths. And so if they don't see these fundamental bands of SO2, then their original detection was wrong, and we need to go back to the drawing board. Look, I'm not suggesting they are, they're probably spot on. But if you get those multiple bands, then that increases the evidence and goes, yes, I've got a secure detection. That's the molecule that it is. And SO2 is interesting because it shows that there's photochemistry going on in the world, which is awesome. Fortunately, there's more lines that the astronomers don't know, which means there's more research for us to do. And I love this slide by Juan, so I'm just going to share it. His PhD, he's developed a high throughput methodology to produce this approximate vibrational spectral data. Maria has definitely helped generate a lot of this data, and she's going on the next step, which is conformance. So that's post Juan's PhD. And then you go from big data to astronomical observations, and we can provide solid directions towards unveiling unknown molecular absorbers in space, as long as someone doesn't do it first. And my concluding remarks are a little bit more on the comp chem side in terms of what method you would do. And I'll finish there. Thank you very much.
Thank you very
Excellent.
much,
Peter's
Laura.
going to clap me.
Thank you for a really wonderful presentation. We've got time for questions. If anyone has questions, please either unmute yourself or pop a question in chat. Oh, yep. Rio, please go ahead.
Hi, this is Rio from the University of Sunshine Coast. Thanks, Laura. It was a really interesting talk. I was just interested in your, I guess, the separation of scaling factors. You justified it on the basis of, comparing experimental and theoretical. But was there a chemical basis to those separations? Or
you mean the 1000 and the 2000 where we did frequency separation? We tested a variety of options. So we tested a variety of options and chose the one. I mean, look, why is 1000 special? It was just the number that you could vary it, but that was giving the best performance. So we tested different things. We didn't really worry too much about the chemistry, except to note that 2000 was sort of probably between functional groups. Yeah.
Okay, so like you couldn't sort of distinguish any trends, say, for example, for stretching frequencies versus bending
actually,
frequencies?
yes, we did do that. Very good point. Oh my goodness, I'm trying to remember data that's in there. We determined whether you wanted to scale stretching frequencies or non-stretching frequencies, and it didn't make a difference. Or at least it didn't make a difference if you frequency separated them as well. And I think we also compared, I did need to look at the paper. I feel like we compared different functional groups as well, or something like that. Yeah.
Okay, cool. Yeah, thanks very much.
I think that's the second paper, but yeah, we did have a bit of a think about that.
All right, cool. Yeah, thank you very much. That's good.
Thank you.
Laura, a traditional approach is to transform into torsions, bends, and stretches and internal coordinates and scale them independently. That can work pretty well. Yeah,
and I think we were definitely aiming at the non-expert user because the experts would do that. But yeah, that's actually some literature we should definitely have a chat about. Thanks, Joe.
Yeah, that's in my Dashin code, for example.
Excellent. I'll chat about it with you. That'd be fantastic. One of the reasons I wanted to present this is because I think there's a wealth of knowledge that COVID meant I didn't have as much opportunity to chat with everyone as we normally would have, and feedback would be great.
Yes, just on the feedback. I popped in the link for the PhysChem division email. Any comments, suggestions, please send through emails. We'd love to communicate.
Probably not on my research, but on the PhysChem division, definitely.
On the PhysChem division. Everyone should have Laura's research emails.
I'll get it. But yes,
I did have one more, much more generic question. How do you find the collaboration process with astronomers in communicating non-technically the challenges around those spectra deconvolution? Because I guess for simple molecules, they have an expectation that it's very easy, but as you start to get to more complex molecules, as you flagged with phosphine and things like this, there's a lot more challenging to be certain what you have.
Yeah, I think, look, it wasn't just me. I think we call it the lineless community. The spectroscopists and computational people that are producing this data to go to the astronomers, I think we've spent a lot of time getting those strong links together. I know one of the most popular presentations I was doing in sort of 2015-ish was literally, what do you need to know to use an XML line list, which was about what are the errors and the uncertainties. And there's a really strong relationship in terms of, they say they don't know how to interpret something, and then we add uncertainties to our data set. And also now with JWST, what's been really exciting is some individuals that did their PhD in the lineless community are now going over and doing exoplanet observations. So there's a really strong community internationally. I know it's strongest in the UK. Australia's not really in the game because we don't have good access to JWST. So we're detecting exoplanets, not doing chemistry on them, unfortunately. Okay. But we'll get there.
Yeah, look, thank you very much.
Thank you very much.
Please, everyone, join me in thanking Laura for a wonderful presentation again.
And I will have to head off at some point, so just apologies to people I'm teaching, but I want to hang around for the first bit of Philip's.
Yes. And Laura, if you could stop sharing so Philip can start, that would be wonderful.
Yeah.
So our next speaker is Dr. Philip Fang. So Philip is a postdoctoral fellow